Hello and welcome to Chapter 9, which is on work, energy, and simple machines. Like momentum, this is going to be one of the main conservation laws that we come across, and it's also going to be very useful for calculating uh, different types of movement without having to use forces if you go on to a more complicated physics class. Uh, but in general, we know the term work, we know the term energy, we know that energy conservation is important just from the way that we store energy and we get energy from the sun and fossil fuels and renewable sources. So this conservation of energy and this being able to change energy from one form to another is going to be important, even if you don't study physics itself. It is important in the future. So the work energy theorem first comes from us defining work, and then we define a couple different types of energy based on our definition of work. So in the same way that the change in momentum comes from a force applied over time, work is a force applied over space. So in that equation, it's given by force times distance, and it is a quantity that is measured in joules in physics in the SI units. It has its own unit. Last lecture, I was talking about momentum, which only is a compound unit, but only has units of kilogram meters per second instead of anything specific. Work and energy have units, uh, particular units for them. So joules, which is the SI unit, calories, which is what you're mostly going to be using in chemistry, and horsepower, which is what you're going to be using if you're talking about the imperial system and you're talking about the English system. So once you do work, once you apply a force over some distance, then that's going to change something called the kinetic energy, which is equal to 1/2 mv squared. So that depends on velocity, and it changes a lot with velocity. So something with twice as much velocity is going to have 4 times as much kinetic energy. So that is kinetic energy can be seen as the energy of movement, whereas potential energy tells us how much work must be done to move against a force, or how much energy is stored by uh, placing an object somewhere where it can be acted upon a force, somewhere where a force is going to uh, cause there to be work done if you let it move. So power, we're just going to go over this briefly. Power is the work that can be done over a time period and is measured in watts, which is 1 joule per second. It is useful quantity. So if you've ever wondered what type of, or if you've ever wondered what the watts in your microwave or in your toaster or in your light bulbs are measuring, it's measuring the amount of work that can be done over a given time. So if you work against gravity and raise, just a second. If you work against gravity and raise a uh raise a couch uh directly up, then the amount of work you did is just going to be equal is going to be equal to the force of gravity times the distance you went over. So it's not going, it's just going to be some quantity that depends on how high up you are. But if you use something with high power, with high horsepower, or oh, actually horsepower is a unit of power, not energy. I'll fix that later, but when you use something with high horsepower or high wattage to lift it up, then it's going to lift it up much faster than something with lower wattage. So it's the ability to do work over a given time and to do work efficiently over a given time. So uh, so now we're going to get to conservation of energy. So in addition to being the work that it takes to uh, work against an outside force or a force that's in the system, potential energy can also be seen as a way to store energy for later use. So if you have the potential chemical energy, or we're talking about mechanical energy, which is movement based rather than chemical or solar or anything like that. But there's something called a gravity battery where you just re pull up a where you pull up a uh, really heavy stone as high up as possible, which increases its potential energy because potential energy goes up the higher up you are, because the higher up you are, the more potential you have to cause movement. So uh, uh, gravitational battery just lifts a huge stone up, and then when you want to release the energy, when you want to cause some movement, to cause electricity or mechanical power or anything like that, then you just release the battery a little bit, lower the battery down a little bit, and that's going to cause an increase in kinetic energy. So the total potential and kinetic energy of a closed system, which again has no outside forces that you're not talking about, is conserved. So the potential energy in this case is highest up here at the top of the roller coaster in this diagram. And then as you go down, all of that, the potential energy goes down, but the kinetic energy is going to go up because the potential energy, because if the total potential and kinetic energy is conserved, if it doesn't change, then that means that as the potential energy goes down, the kinetic energy has to go up. So the kinetic potential energy is at its lowest point, and the kinetic energy is at its highest point here. Whereas once you go a little bit higher, you're going to have velocity kinetic energy that's somewhere in the middle, because the potential energy is somewhere between its highest and its lowest points. So basically, that is conservation of energy in a very mechanical sense. We're going to get into a more, I'm sure we're going to get into a more particular sense eventually, or a more chemical or solar or applicable sense to the modern world. But simple machines make work easier, but are machines that make work easier, but they do not change the amount of work you have to do. So what we have here are a bunch of different examples of levers, where a lever um, is something where you apply a force a farther distance away, So then you to cause there to be a force in the opposite direction doing work. So it doesn't change the amount of work you do. If you look at the top left problem, or the top left diagram, then you'll see that the force that you're applying would cause, so a force applied farther away would do the same amount of work moving a nail or a nail from a bed or nail from a plank. It would do the same amount of work as if you just pulled the nail out without the lever. It's just that because you increase the distance that the lever has to work, this distance, which is the vertical height right here, because you increase that, but you have the same amount of work that you're doing, it decreases the amount of force that you have to apply to get the nail out of the bed, and allows you to do it with just your arm instead of having to use a cattle or a horse or anything like that in order to do it. And then what is happening in the rest of these is also just different types of levers. So this is an axle on the right-hand side. So the axle increases the distance from the distance you have to rotate the big axle around, or the distance you have to create an amount of work that you have to do. So because it increases the distance the same as the lever, versus if you were rotating around the small circle, it decreases the amount of force that you have to apply to pull up a small weight with a force of tension that's going to be greater than the force that you're applying yourself. The same thing is true with this screw in the middle of the this screw in the middle of the page, and that's also similar to what's done with a pulley, where a pulley just by adding extra pulleys, you can decrease the amount of force that it takes to lift something up by the number of loops that you make, the number of extra loops that you make. So for here, for the one on the left, the force that you apply is equal to the force of tension, that's the force that it takes to pull up the block. If you do this middle one, it has two loops instead of one loop, so it takes half as much force, and if you do the third one, it takes a quarter as much force. For reasons that are a little more complicated to get into than just the levers that we're seeing with the wrench, or not the wrench, the crowbar, the screw, and the axle. So that is about how much we're going to get to for simple machines and the very basic principles of conservation of energy. As always, if you have any questions, feel free to reach out, and I will see you again later.